Okay, it's 9:10. Let's start. I'd just like to begin with a reminder that your homework one is due next Friday at midnight. Okay, it should be pretty easy. Looks like some people have submitted. So if you haven't, just go ahead and submit. And grading is really lax. It's 10%, but in general, you'll get it if you submit it. And if you get things wrong, it's fine. The point of the homework, to repeat, is just to get you to reorientate and familiarize with matrix and matrix operations. It's more important that you go through it and get your brain refreshed rather than, let me switch it over, rather than to worry about the points per se. So yeah, just a reminder that the homework one is due next Friday at midnight. Okay, so and if you have any questions about how to submit, just let me know. But in general, you can type your answers in Word and PDF it upload, or you can upload the Word document. Or if you did it in like a Colab using code and all that, you can upload that Jupyter notebook file. That's fine too. In general, just do things electronically and digitally. All right, don't give me paper. Then I'll scan it and then upload it electronically. All right? Okay, so today we're going to talk about single layer perceptrons. Okay, so this is the key topic for today. But I'd just like to quickly rehash and remind everyone about the motivation of why we do neural network, and then the single layer perceptron will make a little bit better sense, okay, but about what we're doing. So to do that, go through some theory a little bit, just to refresh our memories. I sort of talked about this in the first class. In neural networks, okay, why did you do that? Okay, in neural networks, yeah, our key goal basically is to model, okay, model the brain, in this course at least. Okay, but it doesn't have to be the brain, can be any intelligent system, but of course the brain is the big candidate here, and we are very interested in biological plausibility. Is it biologically plausible? Okay, so the first big question is why model? We have talked about this in the first class, but we want to rehash this. Essentially, what we are modeling is we have some input, we put it into some model we call X, and X generates some output. And the idea here is that X is really your brain or any kind of organism, right? You give the organism some inputs and the organism generates some output. Your brain receives input and then it does some computation and then we get some output. An input can be something like that. For example, if you give the brain an input like 1, 1, okay, and then it goes in there, does some weird computation, it spits out an answer and it says 1. All right? And then another kind of input would be maybe you change. Now it's 0, 1 and it says 0. And likewise, you can fill this up. And this is what we'll be sort of dealing with today. Okay? The fact is that you will have 2 input elements, 2 input units. We call them A1, A2. All right? And then it goes into this weird machine, and then it spits out an AJ, an output. Okay? Now, the goal here is that why model? Okay, the answer is, the first thing is we want to see how X behaves. All right? We want to see, like, if we have a model and we think that this model is a model of the brain, then we want to see how this model behaves, and then we want to match it to see if it matches how the brain behaves. Okay? And moreover, this cannot be done, this relationship cannot be determined you can't determine it analytically, meaning we can't use maths. We can't use maths to kind of derive the function to define these input to output mappings. If you could define an analytic mathematical function, then there is no need to model. You just do the math, And that will be the answer, okay? But because the math cannot, or we can't use the math to find out what's the relationship between input to output, we have to try a model, a possible model, and then let it run, and then evaluate the results, all right? So that's one big reason. We could not determine this mapping analytically, so we have to do a model. And then we have to let the model run and then kind of evaluate if our hypothesis is correct. And so by that token, basically, we have a specific hypothesis we call H naught, okay, about X, or how systems like X e.g. brain, people, how they behave. Okay, so one is like, we're not sure, we want to test all sorts of models and let those models play out and then see if it kind of reflects real behavior, all right? The other is, we have a specific model, we have a specific theory, and again, we also want to see how this really plays out. So you can say one is more like a data-driven, observational kind of screening approach, and the other is more of a confirmatory kind of validation theoretical approach, okay? But both would warrant why we want to do modeling, all right? And when we do it, how do we model? I talked about this. First, we form an introduction, a background motivation, a background introduction and motivation, all right? That leads to a hypothesis. Then we design the model design, okay? This involves specifying the architecture, and we will be doing that today, okay? Based on the hypothesis, we come up with a architecture, a designed model, all right? And then the network architecture, the network activation function, okay? And the learning function. These three components, or these three steps for model design, we'll be doing it over and over and over again for different types of models. So today in Perceptron, we will be touching on some of these. Okay, so I'm reiterating this so that later it'll become clearer what we are doing. And then finally, when we have our model design, we can then implement simulations, which means we implement the model on some sort of a data, and then we also want to describe it. How was this simulation ran? How does it work? And what did we see in our simulations? What were the results? So we simulate and we evaluate. So it's like running an experiment and then analyzing, you know, the data and then seeing what the results are, okay? Then finally, of course, after running the simulations and evaluating the results, we can discuss and conclude and make conclusions. Discuss and conclude, make some conclusions, all right? So in implementing these steps, we will be basically doing a neural network model kind of like from the beginning to the end, and in a sense that if you were to write a modeling paper, like purely modeling, just theoretical, in general, and if you read the papers, you will see that this is what they do. They introduce some sort of a motivation, a theoretical one, okay? Then they describe the model, they design it, they run a simulation, and then they conclude or discuss the results. So you see how that mirrored, because most of us probably are more familiar with running real human or animal, you know, experiments. There's some parallels there, right? In real experiments, we also get some theoretical background. We design an experiment, we collect the data, then we analyze the data, and then after that we have a discussion. So in model world, in theory world, formal world, it's the same. It's just that we call it different terms. All right? Okay, any questions about this? Okay, if not, then we will jump to the today's model. We will start with our very first model, which is the single layer perceptron. All right? Now, yeah, okay. Let me talk about the problem first, and then I'll go back and kind of illustrate what the perceptron is, what it looks like, and what's the architecture. Okay, so again, I've put the Jupyter notebook, the collab, on a link on the schedule, so you can go ahead and follow with me on this one. And I also encourage you to open your own Jupyter collab, all right? And we will kind of work iteratively. I'll highlight some problems, and you guys can try it out on your Jupyter. Don't just take my notebook for granted. This is my way of solving the problem, okay? And you can kind of use my way as a consultation kind of a platform. But I do encourage you to do things your way. In fact, at the end of this Jupyter notebook, I leave some things open-ended, and you sort of have to try it, okay? But don't just read through, but do it yourself as I talk through the problem, all right? So in this Jupyter notebook, we go through what is the basic and most simplest of all neural networks. In fact, this is the very first kind of a neural network idea that was implemented by Hinton, and so the guy who won a Nobel Prize for physics, even though he's not a physicist, he's a mathematician or a computational scientist, right? But it reminds us of how actually all our neural systems, our biological systems, are also physical systems, all right? And they implement math. They implement mathematical functions that we can describe using math. And so one of the simplest neural networks is this single layer perceptron. It's single layer because it only has one layer of weights. And we will see it in more concretely later. And we will do it using plain matrix operations. We're not going to do something like import TensorFlow, and then run perceptron, and then just put input, and then that's it. It spits you some output, and you have no idea what it did, okay? We are actually going to go into the mathematics of how it did, what it does, and then you can see better why it behaves the way it behaves. So the best way, really, to learn about perceptrons or single-layer perceptrons is to use it to solve logic gate problems, okay? And so we will define what the problem is. What's a logic gate problem? And this will become the kind of a framework we will use for all the other networks that we will program later on in the course. We will first define the problem, okay? And then after that, we will set up what we call a data table, which defines the problem, all right? And then we will design our network. This is sort of the motivation and background. Defining the problem means coming up with the data table and the hypothesis that matches it, and then followed by the designing and the simulation and the discussion. So defining the problem, excuse me, the easiest logic gate problem is the AND problem, okay? And I have a disclaimer here. In order to simplify this course, we will restrict our problems to binary ones, okay? So it's either input and output states of the neurons are either ones or zeros. They're binary, okay? And we restrict our simulation for now to the case of two binary inputs. So you have two input units, and it gives one output unit, all right? It will get more complicated later on, but for now, as the beginning of the course, this class will just deal with this simple case first. What we want here is an understanding of the mechanism, okay? Not to kind of like challenge ourselves and then don't understand anything, all right? So under this above framing, the classic AND logic gate is characterized by which all inputs are 1. It's an AND logic gate. And if it's an AND logic gate, what it means is that when all inputs are 1, the output is 1, and then 0, output is 0 otherwise for all other cases, all right? So to make it more real life, you can imagine This one, if you've done philosophy, okay, the famous problem, the famous statements. Let's say we have a premise 1, and we call it input 1, okay? The statement is that all humans die, all right? And let's say that this statement is the case where the premise 1 is 1. It's a binary state 1. And then premise 2, okay, input 2 is that Socrates is a human. And again, for this unit 2, the binary state is equal to 1, all right? So if all humans die, if input 1 is 1, if Socrates is a human, input 2 is 1, okay? Then the conclusion, the output, AJ, Socrates will die. Then that is 1 as well, all right? Alternative, or all other possible cases is if input 1 is 0, or input 2 is 0, or both are 0, then the output will be 0. Okay? Think about it. This is just a kind of, this is not the data table yet. This is just to kind of make an ecological example. But I can talk about it in binary terms, but we won't see how it applies in real life. Okay? But in real life, you think about it logically, right? If this is true and this is true, then this must be true. Okay? If any one of that is false, then this one will be false. So that's purely the AND logic mechanism working in our brains. Okay, so here's the challenge. Obviously, we all think that that's correct, that the AND logic in this case is correct, right? Anyone here disagree that if all humans die, Socrates is human, then logically Socrates will die, and you make that computation. As long as I change any one of those premise statements, you will change your output statement, right? All of us here will do that, right? Which means that in your brains right now already is this so-called model that we want to mimic behaviorally. We all do that. How do we do that? Why do we do that? Mathematically, how do we express that? Using neural networks. Okay? So you can replace this with other things. If it rains and I don't like getting wet, then I will bring an umbrella, right? The other case would be if it's not raining or I like getting wet, then yeah, I won't bring an umbrella, right? For example, okay? So you see, you have this frame, this logical frame that's embedded in the way you function. How do we translate that to a neural network kind of operation and see like, hey, yeah, maybe some of our human thoughts and actions and actually can be quantified, expressed formally this way. So, as I said, yeah, in our human reasoning, there's only one case in which the table holds is that basically when the inputs are 1, the output must be 1, otherwise the output will be 0. And so from there, we form this data table, all right? So this data table is basically re-expressing that, the kind of real-life case, in a more simulation formal case, more abstract, but now we know what it means, okay? That we have 2 inputs. When the 2 inputs are on, the output is on, okay? Or when the 2 inputs are true, the output is true. But as long as one of the inputs is not true, then the output would be not true, would be off, okay? All right, so I'm sure you get this. It's very simple, but how do we do it? So the hypothesis is that a system, like our brain, that is just a single layer perceptron, okay? Or that our brain has a single layer perceptron kind of mechanism operating, and it behaves in a way that corresponds to the above logic table, that if we give this system inputs that are either both true, only one true, or both are false, then this system will generate a kind of a output in this pattern, okay? And therefore this system is an AND logic gate. There are other kinds of logic gates, but this system, if it does this, it can be used as an AND logic gate. And so our specific aim, therefore, is to make a single layer perceptron. That's a hypothesis, by the way. For now, I mean, I think sometimes it's like we read it and we think, oh, of course it's all going to work, and I know what's happening, right? But actually, if you take a step back, we actually have, up to this point, we have no guarantee that a single layer perceptron will actually work, can actually do the job, okay? I mean, of course we know that it can, right? But how will we know until we try it, right? So to know for sure, we will make a single layer perceptron with 2 units, and we call this fully connected to a single output. And we will use the above model to implement the AND logic gate. All right? So I'm going to do this visualization a bit later, but let me kind of hash it out a little bit more. If you've read the Agarwal chapter, okay, if you've, then you'll see this kind of format coming out. But if you haven't, well, basically, a perceptron, okay, looks like this. Okay, we deal with the case, as I said, we deal with the case with only 2 inputs. So we have AI1 and AI2. I'm going to use notation here would be just to make things clear, when I say I mean the input layer or the prior layer, okay? And later on we'll have the J layer, which is the output layer. And we always do this kind of, this will be systematic. It will be I, then followed by J, okay? If I do M, then it will be followed by N. If I do P, then it will be followed by Q, etc. All right? So I try to keep that systematic. Moreover, I will do this. It doesn't have to be just 2 inputs. It can be more than 2 inputs, all right? And up to K. Kth unit, okay, of the input layer, okay? And these units, these are the input units. We usually like to draw circles around them, okay, to express that they are nodes, are connected I draw 4 arrows here, but depending on how many K, there will be K arrows, okay? And they are connected to the J unit, J output unit, and we call this AJ, L, because there could be many output units, all right? But for now, let's focus on one. And the notation I'm going to use is that this is weight IJ, sorry. The notation I'm going to use is this is I1, J1, I2, J1, I3, J1, and I4, J1. Okay? And I will change the notation accordingly. If we have more than 2 outputs, then it will be maybe WI1J2. Okay? Right? Okay. And then when these feed into the AJ unit, all right, we will have a pre-activation summation function. This is a pre-activation function. In this case, it is summation sign, meaning it's a summation function, okay? And followed by a activation function. So in other words, a kind of like an output neuron, okay, or output node is actually bifunctional. It receives input and then it operates on it using a pre-activation function, in this case a summation. And then after that, it applies an activation function, which is usually a nonlinear one. And we'll talk about that a little bit later. A nonlinear one which will transform the pre-activation output or the pre-activation value into some other activation value. And that is what goes out as the output signal. And the AJ and the AO sometimes are interchangeable. It depends on whether the AJ is what we are interested in, the activation state, or it leads to some observable behavior, which would be what we technically call the behavioral output, AO, okay? But because of this, I'd like to clarify. So when I say AJ, I mean what is the real output. So I would say AJ is actually equals to AO. And AO is a special case when we say we want to talk about the external behavior. But if we're just talking about the internal node's activity state itself, we talk about AJ, okay? So when we say AJ, we mean what happens after the activation function is applied. But the pre-activation function, we're talking about AJ star, okay? So in other words, pre-activation function gives us AJ star. And then when AJ star is fed into the activation function, you get AJ, okay? And we will apply that later. All right, so this is a perceptron. And we talked about that we have this is the architecture, all right? This is the proposed general architecture. And we have in this case, our activation function is going to be, that we are going to use today is the sine function, all right? So let me yeah. Okay. So we've defined the architecture. We are now going to talk about the activation function. Okay. First, the pre-activation function. This is defined by basically okay, you have some input, you do a dot product as a vector, okay, and you do a dot product with the vector of weights, and you get some scalar pre-activation output, okay, and then the actual activation itself, which is nonlinear. It has to be nonlinear. Okay, we'll call this equation 1. Okay, then the activation function in this case, we want to do something where we achieve this situation. This is AJ star, and this is AJ. We want a situation where this is going to look like this. Okay, it is 0, and we want to keep things binary, and this is theta. Okay, so in other words, the input, the activation function output AJ is 0 when the AJ star is less than some theta value, and it becomes 1, exactly 1, when it is above the theta value. Okay, and to achieve this, we basically do sine of AJ star, the maximum of it, or 0. Call this equation 2. Okay, and or this is what I've just written here is the code way, okay, the code function, and we will apply that. But mathematically or more formal notation, AJ is equals to 1, okay, if AJ star greater than theta, 0 otherwise. Okay, this is equation 2. All right, so we have this, and we have this. This is the formal notation. Okay, so we'll be implementing this architecture and activation function today. Any questions about this expression, this formal expression, and how this max sign function plays out. Okay, let me break it down just in case. Okay, AJ is just the sum of all the inputs, weighted inputs, right? The weighted product inputs summed together. That's AJ star. Sorry. Okay, so that's no problem with equation 1, and I'm writing it in matrix notation, right? So you can also do it like this. Right? It's the same. Okay? In fact, you have that for your homework exercise, right? You have to convert between arithmetic notation and vector array matrix notation. So I've just written equation 1 as a matrix notation. Then it might be that when you sum things up, it can be positive or negative, or it can be very, very positive or close to 0. Okay, whatever the value is, right? But it has a positive or negative sign. All right? So then we take it to be that we don't really care about the magnitude, because as long as it is, in this case, I'm using 0 as theta. I forgot to mention. Okay? As long as it is greater than, as long as it's positive, we don't care how positive it is, right? It will be greater than 0, correct? Okay? So the sign function just basically tells us, is it going to be positive or negative? And then, because what we just want is that, let's say the case where theta is 0, then we just take the maximum of this function. And that will give us an output of either 0 or 1, depending on the sign of the pre-activation output. Okay? What if we don't want the theta to be 0? What if we want the theta to be some arbitrary constant or value? What do we do? Well, the case is we can tweak things a little, and we make AJ equals to max. Let me check. Right. Correct. That's all you do. Okay? Yes. So the pre-activation function minus whatever threshold you use, it doesn't have to be 0, okay, in this case. And again, if that is greater or less than the theta value, right, then it will be positive or negative. And then again, you only care if it's positive or negative, but you don't care by how much. And if it is positive, that means it's greater. And then you compare that against 0, and you take the bigger of the two. Okay? And if it is negative, it will be less than 0, then it will be set to 0. So that's all it is. Okay? So we will apply this now and see how it works on the data table. So if you go back to your the Jupyter notebook, the first step is to visualize the proposed architecture. We are proposing a single layer perceptron that has 2 input units and 1 output unit, and they are fully connected feed forward. Okay? So to visualize it, this is actually optional. This visualize architecture step, let me say, is optional. Okay? But it does help us to kind of get a clear picture about what we're doing. You don't have to do it in code in this way. You can draw it out yourself if it is easier to draw it out yourself. But here's a cool module, GraphViz module, okay, that you guys can use in Python. So from GraphViz, the module has many functions. I imported a particular one, the digraph. I put the link here, and you guys can go and browse it on your free time. Oops, sorry. You can go and browse it on your free time. there's a lot of, it does a lot of cool stuff. So for example, you can do this. Let's see. I think there was a, let's see, features, I think. Nope. License external content. Documentation. I lost links, one of these links, but basically you can see it being applied in many cool ways. Gallery, here it is. Yeah, this one. Yeah, you can use GraphViz to visualize using Markdown language, okay, to visualize, using Python code to visualize all these possible things, many things you can control, okay? So I find that it's a good toolbox to use. There are many others. GraphViz is not the only one, but it's the one that I've used here. So to do that, basically, I define a graph. I call it dot. And in dot, there is an input node, two of them, AI1 and AI2, and then an output node, AJ. And these nodes are connected by edges WI1 to J and WI to J, just like the notation that I used just now, all right? And I put a title just so I know what I'm doing, that this is going to implement or describe or visualize a single layer perceptron that has two inputs and one output. And it looks like that. If you run that code, it looks like that. Okay, any questions here so far? Just simple visualization. Okay, so you can go back and play with it and put more nodes and make things more complicated and then change things like font size and all this and color and all that, all right? But that takes me a lot of time, so I just do this very like basic thing like that, okay? And now that you have AI, you can tell the AI, please use GraphViz to do whatever, right? It will be really cool, all right? Okay, so we have the visualization. Now we define the activation function, and as we said, the equation for it in matrix notation is AJ star, the pre-activation state, is equals to the dot product of the input vector AI with the weights array or weights vector. Okay? No questions there. I assume everyone's pretty familiar by now. We've repeated this many times. And you can express, and then we need the activation function itself, which takes as its parameter the pre-activation state. And this is a case function, which means in the case where it's greater than theta, then the output of this activation function, AJ, is going to be 1. And in the case that it is otherwise, then the output will be 0. And that basically is implemented by this max sign of the dot product minus the theta threshold versus 0 Python code implementation. And this is not a special neural network toolbox thing. This is just mathematics. Okay? This line is just mathematics. It's not from PyTorch. It's not from TensorFlow. It's just from matrix calculation, right? It's the dot product of an input vector, whatever it is. We call it AIS first. Dot product of this input with the weights, okay? NP dot is just a mathematical operation. You can calculate it by hand yourself. You know how to do it, right? NP dot. It is the vector multiplied by the vector, and you get a scalar value, right? And then this scalar value minus another scalar value, which is the threshold. If this scalar value is positive, if the dot product is greater than theta, then this function will give you a positive number, okay, positive. And so that then, because positive is relative to 0, positive number is bigger, so then the AJ will be 1, okay? And if this dot product minus theta is, if the dot product is less than theta, then the sign will be negative. And negative compared to 0, which one is maximum? 0 is higher. So then the output will be 0. So that's what this does. Okay? Now this is the mathematical operation, and I put it as a function. So in Python, you define your own definition or a function like this. I call this function AF, which is activation function. All right? And activation function takes in 3 parameters. Here it takes in AI, Wij, and theta, and these are used in the mathematical operation here in line 2. And the output Aj is returned out of this function. You have to put this line, so that when you later on use this function AF, you have to put in the input vector, the weights vector or array, and the theta value, and you can make this output equals to Aj outside. Okay? All right, so this is the activation function. Any question about how what I'm doing here? Make sense to you? Okay. So then we have our activation function. Let's go back to the data table. All right, because we now need to give this activation function a kind of the input for which to solve the problems. And what's the input here? Well, we create, so remember our data table is basically that the inputs are either 1, 1, 1, 0, 0, 1, or 0, 0. So 2 units, and they have either 1s or 0s according to these sets of these 4 different states. So state 1, 2, 3, and 4. Okay? So, so the input is basically 2 units, 2 input units, but these 2 units have 4 possible states, correct? They can either be 1, 1, 0, 1, 1, 0, or 0, 0. It's 2 units, but 4 possible states. So the input array is basically, the input units basically are a 1 by 2 vector. But because there are 4 possible states, you concatenate these vectors, you get a 4 by 2 array. Correct? On the same page here? The input is actually a 1 by 2 vector. But because we have 4 possible states that we want this network to be able to compute, we get a 4 by 2 array. We just put the 1 by 2 on top, followed by another 1 by 2, followed by another 1 by 2, another 1 by 2. You put it all together, you get a 4 by 2 array. Okay? So that's what we want to create. An input array called AI. We understand it that the inputs are just 2 units, but because we have 4 states, we make it into an array that is basically 1, 1, 1, 0, 0, 1, 0, 0, and the output is a 4 by 2 array. Okay, so don't get confused. It's not that the input is made of 4 by 2 input neurons. It's not. It is still just 2 units as input neurons. But these neurons change states 4 times, or 4 different types of states. So that's why we are creating this. Okay? I'm doing it this way because it's more efficient. You'll see, okay, later. And you can run this code, and basically this is the output you get just to confirm. But you know that this is not necessary. You should understand what this does. Okay? Then we have to specify the weights. All right? Oh, this looks really ugly. I'm going to change it. Sorry. I don't like this kind of mess. Because it's hard to see, and sometimes you get confused. Okay? Yeah. All right. So now you can see it looks a little bit neater. All right? And then the weights. And the weights is going to be a, well, okay. The weights is going to be a 2 by 1 array because, remember, we go back to our visualization. You have 1 by 2 units input, and each input has 1 weight connecting to the output. It's fully connected feed forward. So W has also just 2 so-called two elements, 2 numbers. All right? So the weights we have, right now I'm just going to try I'm giving you the answer 0.8 for, let's say, WI1J, and 0.5 for WI2J, okay? I'm just going to do these two ways, all right? And then I'm going to try a theta of, let's say, 0.8, okay? So in other words, if I go back to the activation function, this one is going to have 0.8 and 0.5, was it? Yeah, 0.8 and 0.5, okay? And this theta is going to be 0.8, okay? And then I have the inputs, which are 11, 10, 01, 00. And now I'm going to see if putting this equation 1 and 2 together, I will get that AJ is 1 when this AJ star is greater than theta and 0 otherwise, okay? Based on my entered parameter values for Wij and theta, okay? So then I'm just going to go ahead and evaluate the model, and here's what it looks like. I first initialize an output array that is, I know that I have 4 different states. So output is only one neuron, one node, right? But it's going to have 4 different states, right? Depending on what state the input neurons are, and those input neurons have 4 different states. So the output must also have 4 different states. So I'm just going to have a placeholder here. I fill it up with zeros, and I make it such that it is having 4 possible places to fill in, okay? Then these are just to create a table for the output results, okay, where I will have input unit 1 state, input unit 2's state, and then what is the, I call estimated AJ output state. And we'll talk more about why I say it's AJ hat and not AJ, okay? This is just markdown way of making a table, okay? And, well, it's not really marked down here. It's just because it's not in the text mode. But this is how I want to make a table, okay? So then I loop over, and here's a little bit of coding here. For those of you who are familiar, super familiar, this is really boring. But those of you who are not, who are, you know, just learning coding, this basically for S in NP A range 0 to AI shape, this line should be pretty easy to read. What this means is that AI.shape 0, okay, you can try it out. In case you don't know, I'm going to, I guess I have to run it to let you see it. Okay, we'll let it load up the engine, the running instance. Okay. So for those of you who don't know, I have AI shape is 4. AI shape 0 is 4 because AI is a 4 by 2 array, okay? So the 0th, the shape will tell me 4 by 2, okay? Shape will tell me 4 by 2. I just want to loop over the number of states, okay? So then I choose AI shape 0. If I do 1, okay, then the answer will be 2, number of units, all right? But I will use AI 0, which is the number of states. So I will loop over the possible states. And this MPA range basically gives me this output, okay? I'm just belaboring this just in case some people are not too familiar with coding, but you will see that this line or this code generates an array that has 0, 1, 2, 3 in it. And in other words, S will at first be 0, and then it will do certain things. Then S will become 1 after it finishes. Then it loop again, S will become 2, and it loops again, S will become, take the value of 3. Okay? So this is just basic looping, just to rehash what's going on here. And so in every loop, what I do is I take the input of the S state and put it into a temporary holding variable I call AIS, which is the current state of the inputs. Because there are 4 possible states, I just choose that loop state, okay? And then I feed it into the AF function. And the AF function, as we remember, takes the input, okay, which is a 1/2 vector now, correct? AIS is now a 1/2 vector. And the weights, which I specified above, which is a 2/1 vector or array, okay, over here. And theta, which is the scalar, okay? And I've put this into the activation function. Because of the way NumPy array works, it might come out as a float, meaning it's got decimal places. And I just don't want to complicate things. So I apply an integer function to make it either 1 or 0 as an integer rather than 1.0 or 0.0, which is fine, you know, but this is just to kind of make things cleaner. And so this is the output, and I put it as the S output for AJ, okay? And it will then do some printing. This is not so efficient. I repeat the function again. But in any case, in fact, I can just do AJS here too if I wanted to. But basically, it will print output each line, and then it will go into the next state, which is if you start at state 0, then it will go to state 1, and then it'll do this, it'll go to state 2, and it'll do it again, state 3, and then that's it, the end. All right, so if I run this, you'll see the output like that. Okay, does this make sense? Anybody confused? Should be pretty straightforward. So is this following the data table? Yeah? Correct? It should, okay? All right, so, and that's it. We have successfully really just implemented a single layer perceptron. It's a neural network. It's the simplest one. Of course, things get more complicated later on, okay? But for now, this is really the core of it, okay? Now, after this, really this is the result you want already, okay? After this is just some other fancy stuff. For example, I can do some fancy plotting. I took this from last week's course on linear algebra, and we played around with Jupyter Notebook. And I can plot it out as a fancy kind of graphic like this. I have 4 states of the input, right? I have state 1, which is 1, 1, state 2, 1, 0, state 3, 0, 1, state 4, 0, 0. My weights are currently set to 0.8 and 0.5, okay? And correspondingly, if I feed these 4 different states of inputs to these neural perceptron weights, I will get output 1 for the state 1, 0, 0, 0 for the rest of the states, okay? So, and then I apply some color scheme to it, make it look fancy, like a heat map and all that kind of stuff, all right? So I can do it this way. I can also do it as a form here, and you guys can take a look at how it's done. It looks like this, okay? And you can, what this form does is it becomes a kind of a instantaneous calculator. So you can play with it. Look, if I do 0, 0, the output is 0, okay? And if I do 0, 1, the output is 0. If I do 1, 1, the output is 1, okay? And I can change my weights here. I can change the threshold value here, and it will update. And I will go through that a little bit later, but that comes in later. But so you can do the simulations, and once you've got the, you think you've got your model down, you can use it by doing some fancy visualization. You can also do some cool app like this, all right? And then comes the next part. And this is where you guys will have to be a bit more active now, all right? So I ask you, is the model performing as expected so far? This model where I have weights 0.8, 0.5, and the threshold 0.8, and I set it up with the architecture as illustrated. Is it performing as expected? Yeah? Okay, no questions there. Now, here's something interesting. How did I decide on these weights? Why did I use 0.8, 0.5, and the threshold 0.8? Don't know. I just told you the answer. So, can we change them? Let's see what happens if we change them, okay? And that's where the app comes in, you see? So, 1, 1, output is 1 if my weights are set like this and the threshold is like this. What if I change the weights to this? Okay? It's not 1 anymore. All right? How do I do that? How do I deal with this? I change the threshold, for example. Okay, so in other words, I can play around with this, all right? And I can try all sorts of numbers, and I see, the table, how it works. Okay? So this is a case of why I run the simulation. I have no idea what numbers to use. I'm just guessing the W weights and the threshold to use, and I'm just throwing random numbers in there, okay? And then every time I throw in there, I see how the network performs, okay? So, and this will come in later because for this class today, we are not talking about the learning function. Remember, we have the 3 things that we have to specify. Architecture, activation function, and the learning rule or the learning function or the updating function. We are not dealing with that today, okay? So, but that's the part where that will tell you how you want to change them, how you want to change the weights. So for today, you are the learning function, okay? You will kind of look at the numbers and then kind of think. You can also sort of do it, I think humans are very powerful, right? You look at this and you know this is going to be this times this plus this times this, and if it's greater than some theta, I will make this 1. You can hold all these numbers in your working memory, and you can kind of guess a set of numbers that you think will work, okay? And that's what this calculator will help you, right? Like you try guessing a few numbers, and you can write down the answer, and then you see, what are the different sets of numbers that will work? And so this will tell you how you might change them. But this is very random and no guarantees, right? So in the next course, classes, lectures, we will then introduce learning rules, okay? All right, so next. So I notice that I said that the output is AJ hat, like this, okay? AJ hat, rather than AJ. So think about it. What we have in the data table is AJ. What we observe, what we want, AJ, okay? What we are doing here is we have a model, we have a simulation, and it gives us some output. And actually, we have no guarantee that the output will be equal to the actual data table output, right? We just hope it will be. So in other words, it can be wrong. It can be off, right? And that's why it is an estimate. It is an AJ hat rather than the actual AJ. Now, to the extent that AJ hat is equals to AJ, then our model is correct, right? But if AJ hat is wrong, for example, now, like if I do the threshold, it's 0.6. Oh, sorry. Oh, it still works like this. Okay. So for example, now AJ hat is not equals to AJ, right? Right? So that means my model is, failed, right? So I use AJ hat because to distinguish what is the output from my model versus what should be the output given the data. All right? So essentially, we want to compare AJ hat with AJ. And that will factor into how we might change the weights, which will factor into the learning rule, which we will talk about in the future as well. Okay? So that's for this part. Now, here's a question. Can someone tell me, all right, we have the pre-activation function, right? So let me go back to this one. Okay. We have the pre-activation function. And that's this fella here. Okay, but then we submit it to an activation function, which is a nonlinear function, which is this fella here. okay? Someone tell me, what happens if we just use the pre-activation function? Why can't we just use the pre-activation function? Why do we need the activation function? Or what happens if we remove the activation function? Make a guess? So let's say, let me formalize it. What if AJ is equals to AI The second case is very complicated, right? More complicated than the first one, right? Why do I need the second case and not just use the first case? Any answers? It won't be binary, yes. But why do we have to make it binary? What's the use of it being binary? Yes? Can you say why we need it to be on and off? Huh? Not really. Not about the computer system. The computer system can handle binary or float numbers fine. I mean, binary at heart, but it can still do, float computation. Think about the implication. If we do not have the second case, so it's not binary anymore, right? And it is just AJ is equals to the product of the weighted nodes activity. Is it a neural network? Is the output AJ indeterminate? As in, do we need to model it? We can, if you've read Eigelwald also, you can take, he probably talks a bit about more detail. Let me remind you what this looks like, okay? Need more space. Let me write it. Because in this form, you will see it very clearly, okay? This is AJ is equals to right? Plus, let's say we have just 2 units, but it's fine, you will see it in just 2 units. Does this remind you of any form? Isn't it? It's just a GRM. It's just a regression. Key is that it's linear. And because it's linear, we do not need to model it. We can absolutely just calculate it. We don't need to simulate it. That's what I mean, right? It's still a model, right? But you don't have to simulate it. You can just apply the MLE, right? Maximum likelihood, or however else you want to do it. And in one shot, you get exactly the weights. You know exactly how to determine this with with all the other model validation tools that come in when you do linear regression. Okay, very powerful, right? Okay, but and this is if you don't have that activation function. Okay, so the activation function basically applies the nonlinear component. It is very critical. is very, very critical. Okay? If we don't have a nonlinear activation function, right, then essentially our neural network model is, we can just calculate it with an n it can be huge, but it's still linear. So you can just calculate it, and then the answer is given. You don't have to actually run it. You don't have to spend all this energy in what we're doing in LLMs to kind of like, well, feed it data and then have it like update and do all this really, really troublesome kind of learn and update. In other words, you don't have to guess those perceptron weights, right? I just asked you, right, when you have, why did I use 0.8 and 0.5 in the weights? Well, I just guessed. My guess could be wrong. For example, in the latest one, where if we changed back, okay, this latest guess, if I use the weight 0.3 and 0.5, it's wrong. And then my output is, my AJ hat is not AJ. So I'm going to have to change my weights again. So I have to learn and then change. I don't have a linear function to tell me what numbers to use. So I have to guess and guess and guess until I reach some where the AJ hat is equals to AJ, right? And I have no idea how I guess or what I did. It's definitely not maximum likelihood. Okay? It's by luck. The luck function. All right? And so, it's troublesome, right? I didn't get the answer by finding the minimum of their error sum square, right? Which I can just, if I use that, I can just calculate using my hand and I get it confirmed with full confidence what the answer is. But when I do it this way, I'm just guessing all the time, okay? And that's because it is nonlinear. I have no idea actually how it will work. I mean, you have some idea because it's so simple. You can guess sort of roughly, but you don't have an analytical way to say it, isn't it? You can just guess any number and they will have worked, but you have no idea why. Or some numbers worked, but you don't have any idea why. You can say why in the sense that, well, they didn't add up to more than theta, but you didn't have a principle for which you can come up with a class of numbers, sort of, by which you can say that they will work or they won't work, okay? I mean, technically you can here in this case, but when things get more complicated, you can't, okay? All right, so if we remove the threshold function, which is the activation function, essentially neural networks, the nonlinear activation function, okay? If you remove it, essentially the neural network becomes a linear regression model, or a very complex one at that. But it's still a regression model, okay? So that's, and in that case, actually you don't gain any computational advantage to a neural network. If it becomes just a linear regression model, then it is just as powerful. It can only solve linear regression problems. Neural networks' power is in the fact that they can solve non-linear problems, okay? And we'll come back to it later. So this activation function is the magic of what drives that the neural network can do what it does, right? Otherwise, we can just use linear regression and solve all these problems. And the fact is that they can't, okay? Linear regressions can't solve these large language model problems, all right? Okay, so that's enough from me, most of it today. And now I'm going to open this time up for you guys to try these simulation problems, okay? So, and I will kind of demo the next one first for you, and then after that, I'll let you guys handle, well, I'll demo the OR problem and the XOR problem for you, and I'll let you handle the N and the N1 and N2 problem yourself on your own time, okay? But the next part of this class, that's what we'll try out, the OR problem and the XOR problem, okay? But before that, we will take a break, and then we'll come back, and then we'll try this out like iteratively, okay? Any questions at this point of the AND gate and the single layer perceptron? And how to implement it in Jupyter, Colab, or Python, or whatever environment. All good? Okay, so let's take a 10-minute break, come back at 10:30, and we will pick up the OR problem, okay? All right. Okay, is it 2:30? Yes, that's 10:30. Yeah. Okay, let's start up again. So this is where things get really interesting, okay? Because we have solved the end problem. We have proven that if you have a single layer perceptron, 2 units, input units, 1 output unit, right, it can solve the end problem, all right? Suggesting that in our brains somewhere, because we do these end logic things, as we suggested, like the Socrates is human problem, right? We can do that. That means there are some single layer perceptron kinds of operations happening in our brain. Now, that doesn't mean that our brain only has these 2 neurons linked to 1 neuron output. What it means, at least fundamentally, is that our brain has 2 node states linked to 1 node, 2 node input states that can transition or link to 1 output node state. What node state means, doesn't necessarily mean 1 neuron, right? A node can actually be made of many, many neurons. It doesn't even have to be like a set of neurons at one time. It can be dynamic. It can be like many, many neurons computing over time, resulting in 1 input node state. Okay? It's just how abstract you want to think of it, but it's just a symbol. It's just a placeholder to say, whatever gave me this state, but that state is either on or off for this input element of the computational graph of the neural network. Okay? And underneath what's actually giving rise to that state, maybe even itself complicated, more perceptrons underneath. So input neuron nodes can themselves be single layer perceptrons feeding into subsequent single layer perceptron, etc., etc., etc. In which case it becomes not a single layer perceptron, it becomes a multi-layer perceptron. Okay, and we'll come to that. So, but the point to appreciate here is that we have solved the AND gate problem using a neural network with this formal process. Okay, then the logical or the natural thing to do would be, well, does my neural network solve other problems? Does my AND gate setup solve other problems? All right? Where does it work? Where does it break? So it's like if my brain can solve the AND, if my brain looks like this, okay, and with this weight settings, can I use these this brain to solve other kinds of problems? Okay? For example, the OR problem. And the OR problem is different from the AND problem by just one very simple thing. Instead of the requirement that the output is 1 only when both inputs are 1, the requirement is now that the output is 1 as long as one of the inputs is 1. All right? So you can then, I leave it to you to translate what that means in real life situation. Okay? This is not a philosophy class, but I'm sure you can find. In life, it's not always an AND problem. There are also OR problems, right? And so this is expressing the OR problem like this. And the only case where the output is 0 or false is when both inputs or both premises are false. Okay, so I'm going to work through things on my own, okay? And I'm going to like take bits from the AND gate and put it here. But I want you guys to try it out yourselves as well in your own notebook. And I'm going to do maybe work for the next 10 to 15 minutes or so. And then we'll see and compare, all right? Or you can compare with what I do. But please go and work it out in your own Jupyter notebook. I'm sure it'll be fun if you can see whether it works or not, okay? Now, I'm going to do it in a different way. And I'm going to use my AND gate calculator, all right? And I'm going to apply the same principle, but I'm going to use the AND gate calculator and modify it. And then I'm going to test whether my AND gate calculator can do an OR gate problem as well. Okay? So this is what I'm going to do next. You guys go ahead, and I'm going to start working. OR gate calculator. Okay, I'm going to modify things a little bit. Okay. You're still working? Okay, let me show you. You can continue working on your own, okay? But let me just show you what I've done. All right? So this is fun. Okay? Well, it's fun for me. I don't know if it's for you, but it's fun for me. Okay? Is that, so we started out with the problem of the end problem. We implemented an architecture, a function, and then we simulated it and we evaluated it. Okay? And we know that that class of problems, the end problem, end logic gate. And now we've graduated, and then we saw that it works. Okay? With those settings, it does it. Now we ask, well, can it do other things? And what other things? Well, what if we switch things up and make the data table like this, an OR problem, OR logic problem? Well, okay, so then let's use the same things that we did for the AND problem, and now we feed it the OR gate problem, okay? So, and all this fancy code is just basically, if you saw what I did, I just copy and paste and reformatted things a little bit, but essentially the weights are the same, 0.8, 0.5. The threshold is the same, 0.8, and the input is the same, 1, 1, 0, 1, 1, 0, 0, 0. Okay? And the question is, does this setup, okay, of these weights, these thresholds, the activation function, and the architecture, and given the same input, because in the OR problem, the inputs are the same, but it's just that the outputs have been changed. Does the same setup for the AND gate give me the same the output that I want for an OR problem? And the answer is, you can see, no, right? If I use these settings, it gives me an AND logic gate output, as expected, of course, right? And it's not going to be able to give me the OR output, of course, right? This is not really anything surprising at all. Kind of expect that, it shouldn't. But so what can we change in the network model so that it, from an AND gate, can we make it into an OR gate? Okay? So this is the OR logic data table that we want. This is what the model AJ hat currently gives us. How do we make AJ hat become like AJ? So here is the instance again. We are back to the same problem is, well, how do we change our weights? How do we change our thresholds? We don't know. We use luck. We just guess. Okay? I mean, there is a principle here, but at least for now, I'm just going to suggest to you that out of lack of a mathematical or a logical, conceptual kind of algorithm, well, we just guess. And so I've set this up so that my calculator, this way I do it, it will instantaneously update with the table that I want, or the table of the model's performance, and also give me some fancy graphics, you know, based on what I already did before. So the AI, the input doesn't change. It's going to be 1, 1, 0, 1, 1, 0, 0, 0. But and that doesn't change because for the OR logic, it's the same input. But the weights I can change. So I'm going to change the weights. You know, let's see. Maybe I guess 0.5, 0.5. What happens? Nope, still 1, 0, 0, 0, okay? I'm going to change it to 0.3. Even worse. Now it's not even an AND logic gate, okay? Now let's see. Okay, going down doesn't help. It was 0.8 before, so I reinstate it. So what happens if I go back up? Okay, seems to be getting better. Okay, there is at least one more 1 here. What if I do like 1? Okay, can I go higher? I can, but does it make a difference? Doesn't seem to. Okay, let's try the other weight. Let's go 0.5 to 0.7, 0.8, 0.9. Oh, it snapped into place. So I'm just guessing. I'm going down for one weight, then going up, and then try the other weight, going down, going up. Okay, so this is what I am doing. I am the learning function. Okay, and I have no reason why I try those numbers except very stupid. I just want to go down, go up for one of the weights one at a time. Okay, all right. So so I am the LLM. Okay, at this moment. All right, and I am telling my network change these weights and then see what happens. It didn't work. Change these weights again, see what happened. It didn't work. It gets closer. Okay, this is a good direction. Follow this direction. Okay, so you can kind of get the feel. Actually, that's what the LLM is doing. It really is doing what I just said. It changed it. It see, oh, is this better? Okay, if it's not, then change direction. Oh, it's better. Okay, let's make it better and go in that direction. Okay, so that's what all these fancy LLMs are doing. Okay, basically you, but on electrical operation. So these sets of weights satisfy my OR logic gate data table. So it's a solution. It's one of the solutions. Okay, and this is just making it convenient so that I can guess and immediately see what happens. Okay, so in your implementation, you don't have to copy mine. You can copy mine if you want, but you might want to do better than me, okay? Because I don't say that my implementation is the best. And certainly I can see where I can improve things and all that, all right? So this is part of coding also. Your code solves the basic problem, but you might want to think about, wait, what if I want to use it in other places? So how do I make things more efficient, more visualization, more salient for me, for other people? Okay, so for example, this makes it easier for me to do this. So I can see that what generally happened is that originally my AND gate weights were 0.8 and 0.5, so they were lower. So what I've done is basically increased the weights, right? So now the weights are 1.3 and 0.9, okay? And suddenly the AND gate, all I did was increase both weights. The AND gate then became an OR gate. Okay? Here's an experiment I want to try again. I'm going to reset 0.8 and with 0.5, right? Goes back to the AND response, right? The AND gate response. So what happened just now? I raised the weights and the AND gate became an OR gate. So here's where, when you do simulations, this is the key. It's not just like, oh, I make it work and then that's it, that's the end of my paper. No. You want to get at the mechanism. You want to understand what's going on. And you notice that, well, I raised my weights and my AND became an OR. Logically, what the weights were doing, if I understand my activation function and my pre-activation function, is the sum of the weighted products, right? If my weights increase, that means the sum of my weighted products increased so that I crossed the threshold, isn't it? And therefore, more ones occurred. So by logic, or by reason, I can do the same thing. I don't have to be so troublesome to raise my weights. I can decrease my threshold, correct? That will be equivalent to me raising my weights. If either I raise my weights or I decrease my threshold. Both will make my activation function more easily become one state rather than a zero state. So this is a hypothesis that developed from my original hypothesis, and now I can run an experiment, a simulation, to try to see if it works. Okay? So increasing weights works. What if I decrease threshold? Okay? So from 0.8, I go to 0.7. Yeah. And it did it faster than me increasing my weights, because I increased my weights, I had to do it one at a time and figure things out. I just now change one parameter and just one step, and I see such a big change. I'm going to go down a little bit more. Still okay? Not yet. Not yet. Ah, it popped. Okay? So I would say this is more efficient than changing weights, is to change your thresholds. Okay? Because weights, I have to change one at a time. But threshold, I just change one and I apply it to all the nodes using this activation function. By the way, it is not necessary that all the nodes have to use the same activation function. In this case, it is, right? I have only one of that threshold function and I use it for all my nodes, okay? But there might be networks where some network use one threshold function and another network use another kind of activation function. But in this case, since I know my network architecture and activation function, I know that by changing it, I can do this. Now, this then brings out something interesting, fundamental about logic gates, the relationship between AND and OR gates. which you guys probably already know. An OR gate is just simply a more relaxed AND gate. Okay? We all know that, right? And you get that intuitively also, right? If I'm very rigid and I require that all the conditions be met before I say that this passes, there's an AND requirement. Everything must be true before this is true. Well, I can be a bit more relaxed, not so rigid. Say, well, as long as one of it is true, I can count it anyway, right? That's more relaxed. Psychologically, it's more relaxed anyway, right? So that's an OR. That's all an OR is, okay? It's just a more relaxed AND. So neurally, what do you think can be possible mechanisms when the brain is in an AND state versus when the brain is in an OR state? I can suggest to you an AND network state in the brain is like this network must be active, this network must be active, just like our neural network, and it must be active above some higher level before I can press an agree button or I say yes or something like that. An OR state probably means some brain network is active and that is enough to make me press the button. What the other brain regions are doing is not important, okay? Or I can make it such that I lower my threshold in my, well, biologically, whatever that means. Maybe I have, lowering threshold probably means like I have increased, let's translate it to biological molecules. I have increased dopamine levels, right? My dopamine now is very high. So any little thing that happens is going to cause me to impulsively buy this, right? Make this purchase, okay? Or I've increased my epinephrine levels. My salience is now very high, right? Any little stimulation is enough to kind of like make me engage some action. Okay? Does that make sense? How we translate from something so simple, so basic, but then we apply it to some neurally plausible mechanism. We then can go and validate it. We can go and run biological experiments and see is there an AND or OR kind of mechanism happening in this organism's brain's responses and matching it to the behavior. Okay, we can design a behavioral brain experiment to validate these kinds of things happening. And I would suggest to you that if you think of things this way, your experiments will be much clearer and you will have more confidence when you make conclusions, right? I know that many of us will run experiments and we're like, we have no idea what the brain response is doing, what the responses mean, okay? And that's why I always urge people to think of things computationally like this, at least at this level, so that when things happen, you actually know how to explain it in some more complete and fundamental sense, all right? Any questions about this, the AND and the OR, like that, and how that we can use it, how we can use these tools to try simulation experiments, how that is linked to real life biological neural experiments. No problem? Okay, let's try something. If you guys are still working on the OR, please carry on, but I'm just going to move on now to the next problem, okay? And that's the XOR problem. The XOR problem, it's called XOR because it's exclusive OR. And it's exclusive OR because you see the data table. The output is 1 exclusively when the inputs is only one of the inputs is the true state or the on state. It's exclusive so that if your inputs are both on or both true, then actually the output is false or off. Okay, so that's XOR. There's the other flip side of the XOR, which is the XNOR. Okay, and NOR, the end there is a NOT gate, meaning whatever is true, if you put a NOT there, becomes false, and whatever is false becomes true. Okay, so if I do an XNOR, then the output would be 1001 instead of 0110. Get it? Okay, it's very simple. All right. Now let's see if our OR gate calculator can perform an XOR problem. So now at this point it's very simple. I'm just going to copy this whole chunk, and I'm going to just paste it there, and I'm going to call this the XOR gate. Okay. I'm going to play it. All right. This is now just the OR data table. Okay, but I want to get it to look like this. How do I do that? Okay, so my OR changed my, in order to get my N to my OR kind of data table, I just have to either increase the weights or I lower my threshold, right? So, but now I see like, wait, my XOR is not so strict, and is not so strict. It's not like there's a lot of on states. It's like half. One of them became 0 again. So maybe it's more strict, more stringent. So, and I've tried it before where I just lower the threshold. So if I remind you, if you go up again, yeah, okay, something like that, 1, 0, 1, 0, but it's not, the 1 and the 0 are not in the right place. So I know what happened just now, I remember, right? You just keep going up, it's just going to become an AND gate, right? So maybe, and that was because I was just modulating the threshold only, or I was modulating the weights only. What if I modulate both the thresholds and the weights? So let's try this out. Let's do, and I'm making it more stringent, so I don't want to make it go higher, I actually want to make it go lower, right? So I'm going to try it. 7, does it work? Nope. 6.6, does it work? 0.5. Does it work? No, it became an AND gate again. Okay? So no matter what, you can go and try it, okay? I can guarantee it's not going to work. Okay? You cannot make an AND or an OR gate to solve, in the single layer perceptron, to solve the XOR logic table problem. Okay? Can anyone tell me why? Why do you think? I mean, if you've read the Agarwal or the other paper, you will know the single perceptron problem. You will know. You suggest why? So we go back to the architecture, okay? This gives you this. And in what other combination is there that you can do? And this goes back to our linear algebra lecture last week. In what linear combination can you get in which this state can be separated, can be distinguished to make it so that it is either 1 or 0 in the dimension space. So let me kind of illustrate the problem with the drawing here. Might be better. When we do an N problem, we are using 2 input units, AI1, AI2, and let's just say that AJ is equals to 1 in the case that it is, where I put a circle with an X like this, and AJ is equals to 0 when I put a circle like this, okay? And let's say this is 1, this is 0. This is when the inputs are 1 and 0, such that this is -1, okay? Yes. I'm just shifting the scales a little bit. I hope you can get it. So because then it's easier to draw, okay? Right, so for the N problem, I'm going to do, let's do N problem. Okay, for the N problem, when AI1 is 0 and AI2 is 0, what is AJ? Right? Okay, and when 1 is 0 and the other one is 1 is 0 and the other one is 0, the end is such that this is the end. This is projection of the states in in a geometric plane. So that's why the linear algebra encourages you to use a geometric, a spatial representation. It's because if you do it this way, you see something very interesting. Okay, I project the input states in relation to the output states like this. And I find that I can do this interesting thing, is that I can draw a line, a straight line, okay? And I can exactly split when the AJ state is on versus when all the other possibilities where the AJ states are off with respect to the dimensions covered by AI1 and AI2. Okay? I can just draw a line and say when AI1 and AI2, they have this whole range of possible responses, this whole area there, okay? And as long as you are on that side of the area, you are on. And when you're on this side of the area, you are off. Very easy. Okay, so that's AND. Let's do OR. For OR, simple. Yep. It's only off when both are off. And in this case, I can also do this. I can also still draw a line. Can I still split the area into two? Yes, I can. Yeah? As long as you are above, or to the upper right of that basis, you are on. On the lower left of the basis, you are off. Okay. Let's try this one. What color should I use? Orange. I want it so that this is on, this is on, this is off, and this is off. Correct? When both are on, the output is off. Okay? So focus on the orange color. Make it more bold so that it's more salient. Okay? Now, can anyone draw a straight line to split? This is like one of those drawing games. Like, can you draw a straight line without lifting your pencil to connect all the dots? That kind of thing. Can anyone draw a straight line to split the X circles with the unfilled circles? And we could tell you there is no basis. You cannot draw a straight line geometrically. What you can do, however, is if you add, and here's a clue to how to solve the XOR problem, okay? Let's say I have a third basis, okay? And I can call it also 1 and 0 and 1. Okay? So now imagine that you can somehow split it so that coming out of the board, move those orange cross out here. Okay? So, and then I'm going to remove them from here. Okay? Can you imagine it? And just, I guess I can just go ahead and erase these. So the orange crosses are no longer on the same, limited to just the same plane on the AI1 and AI2 basis. I have now created an AI3 basis. I've made this three-dimensional. And when I do that, if you can visualize geometrically, this is why it's powerful, all I need to do now is to say that, well, I have, running out of colors, but this will work. I have a okay, so that the whole circles without the x's are on that side of this pink plane. Okay? Whereas the cross circles are outside this side, closer to us on the pink plane, if you can visualize that. Okay? So in other words, by adding another basis, I can solve the XOR problem. I can separate the circles, unfilled circles with the cross circles. And that's the clue, okay, to solve the XOR problem. I'm not going to solve it. I'm going to let you try it this week, okay? And then next week we'll see what your solution is, okay? I think that might be one of the homework. We'll see. I don't know. I forgot, but it might be. And then you can do it on your own anyway. Okay. Any questions about this setup? I've just given you a clue to how you can solve the XOR problem, but I've not really demoed it on how to do it in the neural network case. We will hold it off, let you guys try it and struggle with it, and we can come back to it next week. Okay? All right, but any questions about what I've set up here? And so this is a case where the geometric and spatial understanding of the problem, right, really is powerful because it helps you to give you a clue about what's going on and how you might approach solving it from the geometric sense, and then kind of try to translate it to how this can be implemented in a neural network. Okay? And if you understand this thinking, you will also then can bring it to how LLMs and all these advanced neural networks work also. Literally, those networks weights, and therefore the nodes and their connections are these bases, these hyperdimensional spaces, okay? And how these activate are then used to sum and then apply with the activation function that they give rise to an output state. These output states are locations on these hyperdimensional spaces, okay? And the problem that these neural networks are trying to solve essentially is either how to separate those output states or how to go from one output state to another, okay? So for example, CNN, we will talk about it maybe at the end of the class, convolutional neural network. How do I cluster different output states and separate them from other output states? So that's like object recognition, right? I have all these possible states. How are they clustered together to say, oh, it's a cat state versus a dog state, something else, okay? LLMs, how does my current state in this location then make me move to the next possible state? How do I make my dimensions work so that I can transition from one state to another? Okay, those are geometric. If you use geometric representation, that is essentially the problem. Okay, we're just doing it very simply now with NOR and XOR gates and binary states, because those other states may not be binary. Okay, all right. So that's the XOR. I have copied my XOR gate calculator here, and I'm just going to make a note here that fails. Okay, it fails. So my experiment failed, and then I'm very depressed. I don't know what to do. So yeah, you have a question? Oh, sorry. Thanks. Yeah. I just typed it here. In my XOR gate calculator, it fails. Okay? So then I'm very depressed and I don't know what to do. So I have to go and draw pictures and then like kind of see how to figure it out. And that's not the only way. I mean, for me, geometric way makes a lot of sense, but there are also other ways to say, okay, why it will fail and then how you might possibly solve it. All right? Okay, so that's just presenting it to you. Please go back and try to figure it out. Okay? And I introduce another extension of the problem. Okay? Now we go back to the N problem. Okay? But an extension of it, and it's problem 1. What if my data table is like this? Instead of just one output, okay, I have another output. I have two outputs. And this is also sort of an AND problem, okay? Except that this is a NAND. Okay, so let me this is a NAND case. 0001, okay, is not AND. So NAND. Okay? Can you make a neural network perceptron, single layer perceptron, that will do this? You can. Think about it. I'm sure you can. Think about it. Okay? This is a challenge for you. So I'm not going to solve it. You guys try it out on your own. All right? Again, this is fun. All right, this one is more difficult. Well, XOR was difficult, but this one is also another tricky one. Okay? This is still one output, but now I have 3 inputs. And I still have an AND requirement, which is that all 3 must now be true before my output is true. Okay? Again, I would say this is possible, right? But how would you implement it? Okay? So these are some things. We start from some basic core, and then we just kind of palpate our way, like go this way, and see how far our single layer perceptron goes before it fails. How can we modify it to still work, or no, it can't, all right? So the worst case is the XOR, okay? And that's because it becomes nonlinear in a 2-dimensional basis, basically. And so you need another dimension to make it linearly separable, okay? So that's the mathematical reason for why XOR requires another basis, right? But the rest of these are sort of linearly separable, but you will have to be a bit creative in how you design your architecture, and maybe try out different weights and things like that. Okay, so these exercises here are meant to kind of push your thinking. Okay, so I just want to present this today. Any questions about what we've covered? I believe homework 2. Let me see. Is it also today? Yeah, I will open it later. I haven't opened it yet. But essentially, if you do what we've been doing in class, you will be doing this homework. All right? So by trying whatever you are doing in class, you can copy and paste it into this homework too, and then you can submit it. I will open it maybe later today, and then again, it'll be a 2-week timeline, and I'm sure you guys will be fine. Okay? Any questions? If not, I hope this is fun. It's fun for me to just try it out, okay, and see it work. And let me emphasize that for today, we have not touched on learning functions yet, updating rules, all this, okay? So you are the learning function. You are guessing all these weights and all that. But the point here first is to how do we design it? How do we set up the architecture? What are the limits of the architecture? And then we fix just one activation function. We are using an activation function, but we're just using one activation function. There are many other types of activation function. We might try those out later on, okay? So that's where we're at in this course. So at the end of the course, it will become automatic to you. Whenever I give you a neural network problem, you will automatically think of it as a data table. You will then think of it like, okay, what's my architecture? And then what activation function do I need to put it in? And then when we get to it, what learning functions can I use? And that will be just over and over and over again. That's going to be the frame and the format. Okay, so if no further problems or questions, then I've set this so you guys can refer to it. I believe today the video recording should be okay. I'm sorry about last week's video recording. It was recording just the video, but not the screen. If you guys have taken a look, but you don't have to. Last week's lecture is not so critical anyway. But I believe today will be okay. And then I will upload it to the system for revision and review if you are interested. But I think you guys can sort of figure things out on your own. plus the readings. Just get your hands dirty and get practical application, and you will learn a lot. And so then that will be it for today, and I will see you next week. Yes? Let me see what's up next week. Oh, right, okay, yeah. Next week will be difficult. We will kind of jump one level because we will then be dealing with, this guy is the Nobel Prize winner, shared Nobel Prize with Hinton, Geoffrey Hinton. John Hopfield shared the Nobel Prize with Geoffrey Hinton for discovering or at least creating the Hopfield network, which is an autoencoder, which is an attractor network as well. Okay, it's known by many names. And the key thing about his contribution is that I would say he's the first one, 1982, okay, to demonstrate that a neural network can have memory, like our human memory, okay? And we will talk about that. That's a psychological concept, okay? That's where you're bordering on intelligence, really, okay? Whereas this perceptron is just calculator, right? 1 + 1 = 2, logic gates. But we have something called memory. And what is it? And how does it get implemented in a neural network? And then how does that tell us about what our memory really, how our memory works in reverse as well, okay? So kind of back and forth. We have some idea about how our memory works, we try out, and what we try out kind of also informs us about how our memory works and vice versa. And this is brilliant work. You got to remember that it's 1982. There is no AI yet, so to speak, okay? And no powerful large language models. And John Hopfield took principles from biology and psychology and applied it in mathematics and computational science, and then that's what we got. So please go and read the paper, at least the introduction and a little bit of the methods. The part at the end of the discussion, I know it gets very, very technical and all that. It's okay if you don't understand. You can try reading it. It's okay if you don't understand it. But I think trying to get at the first, the intro and the implementation is pretty important. So do try to read up on Hopfield as much as you can. We will spend a few weeks, maybe 2 to 3 weeks dealing with it. So there's no rush here. So you will note that next week, I will not be doing the Jupyter notebook. I will just be covering the principles of the Hopfield paper. That's all. It might be a short class. It will just talk about theory, okay? But it will be more important for you to read it and of course, finish up what we're doing for the perceptron. And we'll bring that up briefly next week. But for next week, it's critical for you to read the paper, okay? And so that you know what a Hopfield network is. It's a very important network, okay? All right, so that's it for today, and I will see you next week, and we will talk about attractor networks or Hopfield networks or autoencoders. All right? Okay, thanks.